I want you to imagine, just for a second, what it would be like to rely entirely on a material that is, well, violently unstable to manage almost every aspect of your daily life.
Right, which sounds like a terrible idea right out of the gate.
It really does. But picture this metal. It's pale gold, almost like a silver gold in the right light, and it's incredibly soft.
Yeah, super soft.
The melting point is just 28.5 degrees Celsius. So, I mean, if you held a piece in your hand, your body heat would literally melt it into a liquid right there on your palm.
Not that you'd ever want to actually do that.
No, absolutely not. Because if this metal comes into contact with even the slightest bit of water,
Give you to sweat?
right, just the ambient moisture on your skin or like the humidity in the air, it violently explodes.
You did
It
it.
is restless, it's volatile, and it's arguably one of the most impatient elements in the universe. Now, I want you to imagine taking that exact same chaotic substance and using it as the foundational anchor for all of global civilization.
Yeah, it's a massive contradiction.
Yeah.
I mean, we're taking a substance that, on a macroscopic level, is the literal definition of chaos, and we are trusting it to organize our entire reality.
And that is exactly the mission of our deep dive today. We are looking at element 55, which is cesium. We've gone through a massive stack of sources for this one. Scientific data, geological surveys, biological reports.
Some really fascinating philosophical notes in there, too.
Yeah, those were amazing. And we're using all of it to understand this incredible paradox. So, okay, let's unpack this. How does relying on an explosive alkali metal for global stability make any sense? I was looking at our notes, and my first thought was that this sounds like asking a caffeinated toddler to perform delicate surgery.
That is a great visual.
Right. I just don't get the leap from, explodes in humid air to runs the modern world.
Well, I'd actually adjust that analogy just a little bit. We aren't really asking the caffeinated toddler to perform the surgery. We are entirely ignoring the flailing arms and legs on the outside. Instead, we're zooming all the way in to tune into the incredibly steady, perfectly predictable, microscopic rhythm of its heartbeat.
Oh, wow. Okay.
Yeah, to understand how we trust cesium with our most critical infrastructure, we really have to look past that violent surface behavior. We have to look at the mathematical order hiding deep inside its atomic structure.
Right. The structure.
But, to appreciate that order, we first have to understand where this element even came from.
Yeah, I noticed in the geological data that cesium wasn't just like sitting around since the dawn of time. It wasn't forged in the Big Bang.
No, not at all.
Our sources highlight that it's a late generation element, but I gotta be honest, the terminology gets incredibly dense here. It mentions things like supernova nucleosynthesis.
That's a mouthful.
Right, and neutron star mergers. I mean, I know stars fuse elements together, but how do we get from a normal star to something as bizarre as cesium?
It really comes down to energy and pressure. So think of a normal star, like our sun. It's essentially a giant fusion engine.
Okay.
It crushes lighter elements like hydrogen into helium, and that process releases light and heat. And over billions of years, larger stars continue this process. They crush heavier and heavier elements together.
Like a cosmic pressure cooker.
Exactly. But that process hits a brick wall at iron. Fusing iron doesn't release energy, it actually absorbs it.
Oh, weird.
Yeah, so the star's engine basically stalls. Gravity takes over, the star collapses in on itself, and then it detonates in a supernova.
Wait, so the star basically breaks its own engine, explodes, and that explosion is what creates the heavier elements.
That's part of it, yeah. But creating an element as heavy as cesium, which is element 55, requires an even more extreme environment.
More extreme than a supernova.
Yes. And this is where those neutron star mergers come in. When two ultra-dense dead stars collide, they release this massive flood of free neutrons.
Okay, I'm tracking.
And the atoms caught in that collision are bombarded with neutrons so incredibly fast. I mean, we're talking a fraction of a second, that they bulk up into entirely new, heavier elements before they even have a chance to fall apart.
That is wild.
That is exactly how the universe forged cesium. It took multiple cycles of stellar evolution, stars being born and dying in these catastrophic explosions over billions of years just to enrich the cosmos enough to produce a tiny amount of it.
Which totally explains why it is cosmically rare. And looking at the Earthbound surveys in our stack, it's super rare here, too.
Oh, extremely.
Like, it doesn't form massive solid ore bodies the way we find, iron veins or copper mines. It seems to just hide out in very specific, obscure minerals.
Yeah, geologically, its footprint is incredibly elusive. You'll find it locked away in these rare pegmatite rocks, specifically in a mineral called pollucite.
Pollucite, right.
And it's really only concentrated in a few economically viable deposits around the entire world.
Hmm.
Places like Canada, Zimbabwe, Namibia, and Australia.
That's a pretty short list.
It is. Usually it's just hanging around near lithium deposits, basically as a byproduct.
Well, that makes total sense as to why human history completely ignored it for so long. I mean, the
Yeah.
Romans, the ancient Egyptians, they weren't fighting wars over cesium because they couldn't even see it.
Right, they had no idea it was there.
It literally took modern chemistry in the 1860s just to isolate the stuff. But I want to talk about what happens when you do isolate it. Because I'm looking at this chemical diagram in our stack, and it shows cesium's structure.
The electron shell model.
Right. It has this big core of electrons and then just one single lonely electron sitting way out on the very edge of the atom. Why does that one electron turn this metal into such a violent explosive?
That single outer electron is the key to its entire personality. You see, cesium is an alkali metal. It sits in group 1 of the periodic table.
Okay.
And because that one outer electron is orbiting so incredibly far away from the center of the atom, it feels almost no magnetic pull from the nucleus.
Oh, because of all the other electrons in the way.
Exactly. The 54 other electrons orbiting closer to the center, they act like a shield. They block the nucleus's grip. So because it's barely holding on, the atom is absolutely desperate to get rid of it so it can achieve a stable, full inner shell.
Here's where it gets really interesting for me. My way of picturing this, right, is that cesium shedding its outer electron is like someone desperately throwing off a heavy winter coat the exact second they step indoors.
That's a perfect way to put it.
It just cannot wait to react. It's practically screaming to bond with anything it touches.
What's fascinating here is that water provides the perfect opportunity for that. When that pale gold metal meets water, H2O, the reaction is instantaneous.
A coat comes flying off.
Yep, the water molecules just rip that loosely held electron right away. And this chemical exchange produces cesium hydroxide and free hydrogen gas.
Oh, hydrogen gas.
Right, but more importantly, the reaction releases a massive amount of heat in just a fraction of a second.
And heat plus hydrogen gas means
Boom.
a violent ignition.
Yes.
Yeah.
And visually, it's stunning. If you burn cesium, it produces these brilliant electric blue-violet spectral lines. It's energetic, it's completely impulsive.
Wow.
And it really represents this incredible cosmic irony.
Mm.
You have an element that required billions of years and colliding dead stars to forge.
Yeah.
It gets trapped in rare rocks, completely ignored by humanity for thousands of years. It just sat there. It waited out the entire agricultural revolution, the industrial revolution, just so the modern information age could finally dig it up and give it a purpose.
So let's trace how that transition actually happens, because I'm still stuck on this. How does this impatient, explosive rock become the invisible heartbeat of our entire modern civilization?
It's quite elite.
It is. If this stuff violently explodes when it touches the moisture in a humid room, how on earth are we using it to run our financial systems? Are there just tiny bombs ticking away in bank servers?
No, thankfully, no.
No.
This is where we move from that chaotic outside to the mathematical inside. We tame cesium by isolating it.
Isolating it how?
Well, in an atomic clock, scientists take a tiny, tiny amount of the stable isotope, which is cesium-133. They heat it up so it becomes a gas, and then they shoot it through a vacuum tube.
Okay, so a pure vacuum. No water, no air.
Exactly. Inside that vacuum, it can't react with anything. It can't explode. So instead, scientists can focus entirely on the internal mechanics of the atom. Remember that single outer electron we just talked about?
The heavy winter coat it wants to throw off?
Exactly that one.
Yeah.
So even though it's loosely held, it still interacts with the core of the atom. It has a tiny magnetic spin.
Okay.
And if you hit that atom with the exact right frequency of microwave energy, that single electron will actually flip its magnetic state. It absorbs the energy, it flips, and then it drops back down, releasing the energy.
Wait, like finding the exact resonant pitch that causes a wine glass to vibrate and shatter?
Yes, that is a phenomenal way to visualize it. Every atom has a natural resonant frequency. And for cesium-133, that frequency is incredibly specific.
Yes.
It only reacts if you hit it with microwaves oscillating exactly 9,192,631,770 times a second.
That is insane.
If the frequency is off by even a fraction of a hertz, the atom does absolutely nothing.
That number, nearly 9.2 billion vibrations, that is the magic number I keep seeing everywhere in the notes, because scientists didn't just, measure that vibration. They used it to completely redefine human existence.
It really did.
The international definition of 1 second is no longer based on the Earth's rotation around the sun.
No, because it turns out the Earth is actually a rather sloppy timekeeper.
Really?
Oh, yeah. It wobbles on its axis, its rotation slows down due to the moon's gravity. Even earthquakes can actually change the length of a day by fractions of a millisecond.
Wow, I had no idea about the earthquake part.
Yeah, so as our technology advanced in the mid-20th century, especially with stuff like radar and telecommunications, astronomical time simply wasn't precise enough anymore.
We needed something absolute.
Exactly. So the international scientific community agreed. 1 second is officially defined as exactly 9,192,631,770 of those microwave transitions of the cesium atom.
So what does this all mean for us? Because, we always like to bring this down to a normal Tuesday for you, the listener. Let's say I walk out of a coffee shop, I tap my credit card to pay for a latte, and then I pull out my phone to order a rideshare. How is cesium involved in any of that?
Well, let's start with the rideshare and your GPS. We tend to think of GPS as just a map telling us where we are, right?
Yeah, just a blue dot on a screen.
But GPS is actually just a giant, incredibly precise clock. There are satellites orbiting the Earth, and inside those satellites are cesium atomic clocks.
Oh, wow. Okay.
And they're constantly broadcasting a signal that basically says, I am satellite X, and it is exactly this time down to the nanosecond.
So my phone is just receiving those timestamps from multiple different satellites.
Right, and it's doing a bunch of math. Your phone calculates exactly how long the signal took to travel from the satellite to your device.
Because radio waves travel at a constant speed.
Exactly, the speed of light. So time equals distance. By measuring the time delay from 4 different satellites, your phone triangulates your exact position on the globe.
But why does the clock itself need to be that microscopic and precise? Who cares if the clock on the satellite is off by a tiny fraction of a second? Does it really matter?
It matters immensely because of how fast light travels. In 1/1000th of a second, just 1 nanosecond, light travels about 1 foot.
Okay.
So if the atomic clock on that satellite is off by just 1 single millisecond, your GPS calculation will be off by roughly 186 miles.
Wait, 186 miles?
Yep. Your phone would think you were standing in the middle of the ocean.
Okay, that definitely puts it into perspective. Wow. And what about tapping my credit card for the coffee?
Financial transactions require that exact same ultra-precise time stamping. Every single day, trillions of dollars flow across global networks in high-frequency trading and standard banking.
Right.
If those computer servers aren't perfectly synchronized to the exact same microsecond, data packets collide, money gets duplicated, and the whole system opens itself up to massive fraud.
That sounds like a nightmare.
It would be. The global banking system relies entirely on time signals derived from those exact same cesium clocks to keep every server on the planet in perfect lockstep.
The reports in our stack classify this under dependency tiers. And economically, they list cesium as a Tier 3 resource, which means biologically we don't need it. We won't physically perish without it.
Right.
But for technological precision, it is absolutely Tier 1. It's essential. Without it, telecommunications fragment, cellular networks drop calls because they can't synchronize data handoffs, power grids face synchronization failures. We would literally lose the defining characteristic of the modern age.
We really would. We took the universe's most impatient substance and used its internal heartbeat to enforce order on our chaotic reality.
Yeah.
It's really a stunning achievement.
It really is.
But we do need to look at the other side of the coin here, because the sources also dedicate a pretty significant portion to the biological and environmental realities of this element.
Right. You mentioned biologically we don't need it. And the notes say life completely bypassed element 55 during evolution. Our DNA, our blood, our nerves, none of it requires cesium to function.
None of it.
But then the environmental reports are full of these studies about ecosystems and animals absorbing it. So if life doesn't need it, why are living things taking it in?
Well, life is incredibly complex, but it can be tricked by basic chemistry. We mentioned earlier that cesium is an alkali metal in group 1 of the periodic table, right?
Yeah.
If you look straight up that exact same column, you'll find potassium.
And potassium is absolutely vital. Our bodies need it to regulate heartbeats, fire nerve signals, manage muscle contractions. We need it to live.
Exactly. And because cesium and potassium sit in the same chemical family, They share very similar properties, they have similar atomic sizes, and they both have that single outer electron to give away, which means they carry the exact same chemical charge.
Okay, I think I see where this is going.
Yeah, so when a plant's roots are pulling nutrients from the soil, or an animal's cellular pumps are trying to absorb electrolytes, they are constantly searching for potassium.
Right.
But the biological filters aren't perfect. When cesium is present, the cellular doorways literally can't tell the difference. They just see a positively charged ion of the right size, and they pull it inside.
It's essentially a biological Trojan horse.
That's exactly what it is.
It just sneaks into living tissues by wearing a potassium disguise. Now, if a plant or an animal absorbs the stable version we've been talking about, cesium-133, what actually happens?
Well, stable cesium isn't highly toxic in trace amounts. It's a mimic, sure, but it doesn't actively destroy the tissue.
Okay, that's good.
But this raises an important question, because the real danger, and the reason those environmental reports are so dense, arises with its radioactive isotope, which is cesium-137.
Right, and I noticed that 137 isn't something you typically find just hanging around in nature. Where does it come from? Neutron stars again?
No, this isotope is entirely a product of human engineering. Cesium-137 is a direct byproduct of nuclear fission.
Oh, wow, okay.
Yeah, when we split uranium-235 atoms inside a nuclear reactor or, during the detonation of an atomic weapon, the heavy uranium atom cleaves into smaller, highly radioactive fragments.
And cesium-137 is one of those fragments.
Yes, it is one of the most common pieces left over.
Which brings us to the contamination zones mentioned in the notes. They specifically talk about the Chernobyl and Fukushima Daiichi nuclear disasters.
Exactly. When a disaster like that occurs, it releases cesium-137 into the air. And because of its chemical nature, it doesn't just sit inertly on the ground.
Right, because it reacts so easily.
Right. It is highly water-soluble.
Yeah.
So it gets into the rain, it washes into the soil, and then that Trojan horse mechanism kicks in.
Oh, no.
The contaminated soil is absorbed by the grass is eaten by herbivores, the herbivores are eaten by carnivores, the radioactive isotope basically bioaccumulates, moving up the entire food web and settling deep into muscle tissue.
And because the notes say it has a half-life of about 30 years, it stays radioactive and dangerous in that ecosystem for generations.
It really does.
It perfectly represents the dual-use nature of the atomic age, doesn't it? Like, on one hand, our mastery over the atom allows us to isolate the stable isotope and build these quantum sensors and atomic clocks that guide satellites through space, which is just the peak of human ingenuity.
It absolutely is.
But on the other hand, splitting the atom creates this dangerous radioactive twin that renders land completely uninhabitable and demands centuries of environmental monitoring.
It is the ultimate double-edged sword of scientific advancement. And, when you synthesize all of this, it is deeply profound to reflect on what humanity's relationship with cesium actually represents. If you look back at the broad history of human civilization, it is at its core a history of synchronization.
I really want to walk through that timeline because it really puts our current era into perspective. If you look at ancient societies, their synchronization was entirely tied to the slow, messy physical world.
Right, they depended on the seasons.
Exactly. You plant when it gets warm, you harvest when it gets cold. It was very simple.
But as populations grew and formed these massive agricultural empires, they needed tighter coordination. They began mapping the stars and the moon, depending on calendars, to organize taxation and religious festivals.
Right, and then the Industrial Revolution hit. And suddenly you have steam trains running between cities on a strict schedule. You have factories needing hundreds of workers to show up for synchronized shifts.
Right, calendars just weren't precise enough anymore.
No, not at all. So society shifted its dependence to mechanical clocks, the physical ticking of gears and springs.
And finally, we arrive at the modern digital civilization. A mechanical gear is vastly too slow to manage fiber optic data packets traveling at the speed of light.
Right.
So we depend on atomic clocks. The evolution of human synchronization is this constant, relentless drill down into ever tighter precision.
From months to days to minutes and now to nanoseconds.
Exactly. And we achieve that ultimate precision by taking one of the most reactive, inherently chaotic substances the universe could forge and isolating its internal rhythm.
It is such a beautiful irony, isn't it? Chaos outside, unyielding precision inside. It perfectly mirrors human civilization in a way. I mean, we live in this messy, unpredictable world, but we rely entirely on these invisible, perfectly ordered atomic systems just to keep the lights on and the data flowing.
Yeah, I think the biggest takeaway for anyone listening is to just pause and reflect on the invisible infrastructure of our daily lives. What stands out to you about how much trust we place in a realm we cannot even see. We go about our days, swiping credit cards, following GPS directions, and we are entirely unaware that the cohesion of our society rests on the predictable vibration of a rare, pale gold metal suspended in a vacuum chamber.
It's wild to really sit with that thought, and it leaves me with one final question. Something for you to really chew on after you finish listening to this deep dive today. We've spent this entire time talking about how we mastered time using this element, but I wonder if our entire modern world, from our high-speed financial markets to our digital social interactions, even down to the very routes we drive, is perfectly synchronized to the relentless 9 billion beat per second rhythm of a single atomic element. What happens to our own human experience of time? Are we truly mastering time through cesium, or have we simply surrendered our natural, messy human rhythms to the metronomic ticking of an impatient metal?